Hi everyone, how you doing? So my name's Emma and today we're going to make a lava lamp that's going to last about 5 to 10 minutes and we're going to do it at home using materials that can be commonly found around the house or can even bought pretty inexpensively like at the Dollar Tree. So the objective of today's experiment is to better understand density and polarity. And we're going to do this using everyday simple ingredients found around the home. Okay, so just like in the last video, we always want to suit up in our personal protective equipment, aka PPE, because lab safety is the most important. Today, I'll be wearing my safety goggles, nitrile gloves, closed-toe shoes, and clothing that fully covers my legs, and a long-sleeve garment like a lab coat, but I don't have one, to cover my everyday clothes. Okay, so while today's materials are everyday household items that are rather innocuous and may seem like they weren't practicing lab safety, it's always good practice to practice good and appropriate lab safety, regardless of how comfortable you may feel or the perceived risk assessment. So in doing so, it'll help build a force of habit or like muscle memory and practicing lab safety consistently and appropriately. Since we're working with liquids today, I'd recommend being extra careful and trying to do this experiment away from your computer or out of the splash zone. Computers aren't really known to be liquid friendly and can be pretty expensive to replace or fix. So I just laid down a quick little plastic cover over the base of my laptop to help protect it. It's actually a little keyboard cover. Okay. All right. So what we're going to do now, we are going to need a clean plastic bottle, cooking oil of some sort, some water, some food coloring, optional glitter, and an Alka-Seltzer tablet. So I grabbed a plastic bottle from my recycling bin and rinsed it out with some soap and water. I'm going to be using a 20-ounce bottle today and something with a large opening because I find it easier to work with bottles with larger openings. If you're using a bottle with a smaller opening, like a soda bottle, you might want to use a funnel because it'll make it easier inserting things into the bottle. All right, so today we have peanut oil that I'll be using in today's experiment. But if all you have or find to use is vegetable oil, canola oil, sunflower oil, olive oil, or a mix of cooking oils, don't worry, those will work too. Okay, so everyday tap water will work totally fine or wherever you get your water source from, just no salt water. And I have some red food coloring here and some glitter because glitter always makes life more fabulous. If you don't want to use glitter in your lava lamp, that's okay too. You can use just the food coloring or a mixture of food colors. You know, just remember that the colors will blend together. All right, and an Alka-Seltzer tablet. Please feel free to use the generic version because both will work. All right, so let's fill our plastic water bottle about 1/4 of the way with our water. Since this bottle is 12 ounces, it'd be 5 ounces. But you can also free eyeball it and guesstimate what 1/4 would be like. So as you can see here, I have marked right off in black marker on my plastic bottle about 1/4 of a guesstimate. Okay, now we're going to fill our plastic bottle 3/4 of the way with oil. Since our bottle is 20 ounces, 3/4 of the way is 15 ounces. You can also feel free to eyeball it and guesstimate what 3/4 would be. Now, as you can see here, I've marked that right off in red mark on the plastic bottle of the 3/4 guesstimate. All right. I made a little bit of a mess, so just wiping it off. All right, so check this out. As you can see, the water and the oil are refusing to mix together. You may be like, hey, what's going on? I've seen this before in some salad dressings or when I was cooking or my mom or dad was cooking, and though they just did a bad job of making it or they didn't mix it thoroughly enough. I totally thought the same thing before, but it's actually pretty cool what happens. The oil and water don't mix because it happens with all oils and waters. You'll notice that the oil stays above the water because it's actually lighter than the water. The reason behind this is that the oil is lighter than the water is called density. Now, density is in which the ratio of mass to volume. The formula for density is as follows. D equal M over V. The D stands for density, and the M stands for mass, and the V stands for volume. We use the SI, or Standard International, derived unit for density, known as kilograms per cubic meter. But since this is a pretty large for most common uses, we like to use the grams per cubic meter, aka G/cm cubed. So, what's neat about the cubic centimeter is that actually equals grams per milliliter. As you can see right here. So you're probably wondering, no matter how hard I try, oil and water are going to mix? Well, the reason why oil and water don't mix is because of intermolecular polarity. That means that the water molecules are attracted to other water molecules and can form little drops. They get along just fine and can loosely bond together, aka form drops. This is like how magnets are attracted to one another. Oil molecules are attracted to other oil molecules, but the structures of the two molecules, water and oil, do not allow them to bond together. So, as a result, we notice that oil floats on top of water because in addition to not mixing with water, oil has a lower density than water. That is, given equal volumes, emphasis on equal volumes, of the two liquids, in this case oil and water, the oil will have a smaller mass than that of the water. Okay, so now we're going to add a few drops of food coloring, about 5 to 10 drops. You can also add a few drops of whatever colors you want. I'm just going to use red because it's my favorite color. Now just remember, if you're adding multiple colors, they will mix together. Just going to put this back over here to make sure that it doesn't spill because cleaning up food coloring is never fun. All right. And because I absolutely love glitter, I'm just going to add a little pinch to the bottle. But you know, if you're not a fan of glitter, that's fine too. You don't have to use glitter in this experiment. I just absolutely love glitter and it's a reason to use it. Boop. Okay. So now we're going to take our Alka-Seltzer tablet and break it up into a few pieces. You can do this manually with your hands as they're pretty easy to break up. Or you can very, very gently step on it with your shoes on or with a pair of sandals or your indoor shoes while it's in a sealed package just so it doesn't get everywhere. Just so you can break it up a bit easier. Now, you're going to take the broken tablet and drop it in. Okay, so now that we've added our broken Alka-Seltzer tablet, it's sinking to the bottom. And we can see it starting to dissolve with those bubbles coming right up. The Alka-Seltzer tablet sank to the bottom where the water is, and it's dissolving in the water. And as we remember from before, the water is at the bottom of the bottle because it has a higher density than oil, meaning that it weighs a bit more than oil, so it's going to sit below the oil. As the Alka-Seltzer tablet dissolves in the water, it's creating gas. The ingredients in Alka-Seltzer combine with water to form a gas called carbon dioxide, aka CO2. The oil and Alka-Seltzer do not combine in this way. So you're probably asking, what are the ingredients of Alka-Seltzer tablet? Totally there with you. So Alka-Seltzer tablets actually contain a mixture of ingredients. One is called aspirin, aka acetylsalicylic acid, sodium bicarbonate, and citric acid. When these ingredients from the Alka-Seltzer tablet come into contact with water, the sodium bicarbonate, aka NaHCO3, and citric acid react to form a carbon dioxide gas. Now, they also react to form amongst other products. So, in a one-way reaction, as we can see here with the arrow facing only in one way, we can see that we have 3 NaHCO3 as an aqueous solution plus H3C6H5O7 as an aqueous solution, producing 3 CO2 as a gas plus 3 H2O as a liquid, and Na3C6H5O7 as an aqueous solution. And here we can view our balanced equation. Okay. So now we have Alka-Seltzer tablets sink through the vegetable oil until they reach the layer of colored water. When the Alka-Seltzer dissolves in the water and forms a gas called carbon dioxide, aka CO2, the gas is lighter, aka less density, than the water and oil, so bubbles up, taking a bit of the colored water along with it as it moves to the oil layer. As we saw with the carbon dioxide, bubbles rose because they are less dense than the water and the oil. They floated through the oil layer to the top of the bottle and took some colored water with it and popped. When the bubbles reached the top, they popped and released the carbon dioxide, aka CO2, gas contained, and the colored water sunk back down to the bottom, as they're now without the carbon dioxide gas, thereby making the density the same as the colored water. The release of the carbon dioxide, aka CO2, in the atmosphere results in a weight loss after the reaction. So we have HCO3 as an aqueous solution plus hydrogen atoms as an aqueous solution plus H2O as a liquid and carbon dioxide as a gas. All right. As the tablet dissolves in the water, the sodium bicarbonate undergoes an acid-base reaction with the acids. The acids that I'm speaking of specifically in the Alka-Seltzer are the citric acid and the aspirin. Okay, so as we mentioned before, one tablet of Alka-Seltzer can make this process go on for about 5 to 10 minutes, and then it stops. Since we were about 10 minutes previously, it has since stopped. Yep, it stopped, a couple bubbles left, but more or less has stopped. All right, so why does it stop? Well, it's because of the limiting reactant. Now, a limiting reactant is the reactant used up first in a reaction. It's called a limiting reactant because the amount of this reactant limits the amount of the product that can form. When all the limiting reactant has been consumed, no more product can be formed. So basically, the acids originally contained in our Alka-Seltzer tablet weren't enough to neutralize all the sodium bicarbonate, aka NaHCO3. So by dissolving the tablet in water, the sodium bicarbonate, aka NaHCO3, is in excess, and the acid, as emitted by hydrogen atoms, aka H+, is the limiting reactant. Only a limited amount of sodium bicarbonate, aka NaHCO3, can be reacted. But how do we know which reactant for sure is limiting? Stoichiometry. We're going to convert each of the reactant masses to moles. Then we're going to use the balanced equation to write the necessary stoichiometry conversion factor and determine which reactant is limiting. When we're going to use the balanced equation to write the stoichiometric conversion factors to determine the number of moles of excess reactant remaining and the number of moles of carbon dioxide produced. Finally, we will use the appropriate molar masses to convert moles of excess reactant and moles of carbon dioxide to grams. All right, so let's start. So according to mole mass relationship, the quantity that reacted can be calculated using the weight loss. So the formation of CO2, aka carbon dioxide, causes the trademark fizzing that we saw when the tablets were dropped into the water. As the Alka-Seltzer tablet contains 1.700 grams of sodium bicarbonate and 1.000 grams of citric acid. So we're going to get our molar masses. Voila. We have sodium bicarbonate, our NaHCO3. Molar mass is 84.01 grams per mole. We have citric acid, or H3C6H5O7. Molar mass is 192.12 grams per mole. And then we have carbon dioxide, or CO2, molar mass, which is 44.01 grams per mole. All right, now we're going to bring it back to our balanced equation from earlier. We have 3 NaHCO3 as an aqueous solution, which then combines with H3C6H5O7 as an aqueous solution, which then, as we see here, the red line, produces 3 CO2 grams as a gas, back up. 3 CO2 as a gas plus 3 H2O as a liquid plus Na3C6H5O7 as an aqueous solution. All right, so we can tell in this equation we have 3 moles of sodium bicarbonate, aka NaHCO3, which is about equal to 1 mole of citric acid, aka H3C6H5O7. 3 moles of sodium bicarbonate, aka NaHCO3, which is about equal to 3 moles of carbon dioxide, or CO2. 1 mole of citric acid, aka H3C6H5O7, is equal to about 3 moles of carbon dioxide, aka CO2. All right, so the necessary stoichiometric conversions factors are therefore this. All right, now we're going to do some basic math. To determine which reactant is limiting, we're going to calculate the amount of citric acid necessary to react completely with the 0.02024 moles sodium bicarbonate we just calculated right here. The amount of H3C6H5O7, aka citric acid, required to react with 0.02024 moles of NaHCO3, aka sodium bicarbonate, is more than our Alka-Seltzer tablet contains. Therefore, citric acid is the limiting reactant and sodium bicarbonate is the excess reactant. All right. So now we're going to determine the mass of excess reactant, NaHCO3, or sodium bicarbonate, as we just mentioned, left over. First, we calculate the amount of NaHCO3, aka sodium bicarbonate, that will react. So there will be 0.01562 moles of NaHCO3, aka sodium bicarbonate, that's going to be consumed, leaving us 0.00462 moles of sodium bicarbonate unreacted. Now we're going to convert this number over to grams. All right. So you can see here we have 0.388 grams of the sodium bicarbonate that was converted. So we are going to figure out how much carbon dioxide was actually produced. We first calculated the number of moles of carbon dioxide produced from the number of moles of limiting reactant, which is citric acid consumed. And then we're going to take that amount of carbon dioxide produced and convert that amount to grams. We did that. So this winds up being right here of our amount, our moles of carbon dioxide. All right, beautiful. So now we're finished. Everything. And we know that we have our citric acid is our limiting reactant in this experiment. And that we had 0.388 grams of sodium bicarbonate remaining unreacted in our experiments. And we had only 0.6874 grams of carbon dioxide produced in our experiment. All right, well, thanks so much for coming today.